Thank you for invitation. I would like to represent the two scientific teams that consist of scientists from Polish University of Opole and Ukrainian Zabolotny Institute of Microbiology and Virology of National Academy of Sciences of Ukraine. And my report devoted to the stereometric redox gradient in redox locality for the integrated biotechnology. Short characteristic of the problem. It is obvious that nowadays we have the huge multi-component contamination of environment by different toxic and dangerous compounds. And the best example, the best model for this illustration are the dumps. Why they are so dangerous? Because due to the spontaneous decaying of polymers take place forming of very toxic gases and liquid products. All of these gases, such as carbon dioxide, methane, ammonium, hydrogen sulfide, and so on, they are simultaneously toxic gases and greenhouse gases. Close to these toxic compounds, soluble end products of spontaneous decaying of organic polymers. There are wide range of toxic acids, alcohols. And what is the most dangerous that the organic acids mobilize the metals in these dumps. And due to this negative effect, the toxic metals involved in the biological cycles. So let's summarize that nowadays we have the problem with multi-component solid waste and metal-containing wastewater. And as an end result, we have the synthesis of a wide range of poison gases, liquid poisons, and results of this, unfortunately, ecosystem degradation. On the basis of our approach, one can obtain the fast degradation of solid waste, fast degradation of liquid waste, obtaining the ecologically pure energy carriers such as hydrogen, molecular hydrogen, and metal concentrate. So our strategical approach is based on the combination of thermodynamic prediction and microbial metabolism regulation to obtain the desired effect. First of all, short explanation. What does it mean, the practical applying of thermodynamic prediction? Here you can see the diagram of stability of chromium compounds in the coordinate pH. It is a horizontal line and vertical redox potential. And it is obviously that in the high potential zone, left brown color, red-brown color, toxic soluble bichromate compounds. At the right side, yellow zone, toxic chromate compounds. And the main idea of the practical applying of the thermodynamic prognosis, first of all, evaluate qualitative and quantitative evaluation of zones of stability of each compounds, and then what shall we do to destabilize these compounds. On the example of chromase, it is obviously that chemical or, for example, a microbiological reduction of chromium 6 compound lead to the forming insoluble, irreversible insoluble chromium 3 hydroxide. And it is obviously because it is insoluble, it is non-toxic. Another example, if we have the problem with the soluble chromo 3 plus cations, so, it is obviously that increase of pH give us close effect, forming of chromium 3 hydroxide. And it is obviously, for our opinion, that most suitable method for the destabilization of toxic compounds is applying of the microorganism. And it obviously that microbial reduction of chromium 3, chromium 6 compounds lead to the forming non-toxic chromium 3 hydroxide. Here you can see the thermodynamic evaluation of the zone of the potential metabolic activity of microorganism. It is close to the zone of water stability in coordinate pH and H. The upper limit of water stability is plus 814 millivolts, and the down lower limit is minus 415 millivolts, and it is obviously that all biodiversity of microbial metabolism only possible in the zone of the water stability zone from plus 814 millivolts down to minus 415 millivolts. Then these diagrams show us that anaerobic degradation, hydrogen fermentation, is the most suitable for the degradation of animal and plant polymers origin. And this hydrogen fermentation need low potential conditions, minus 415 millivolts, and pH close to 7. So, on the basis of this thermodynamic prognosis, we obtained the conditions that maximal accelerate the degradation of solid ecologically toxic compounds. And here you can see the example of testing and application of this thermodynamic prediction. First of all, I would like to emphasize that in the natural conditions, in the dumps, the organic solid matter decrease in mass only in 2 times at 10 years. So it is obviously that this spontaneous decaying is very slow process. Due to the applying of our thermodynamic prognosis, our technological cycle was decreased only to 14 days. And at this very short period, we obtain the solid waste degradation in 20 times in mass and in volume. Simultaneously, we obtained the energy yield, gaseous energy yield, such as 27 liters of hydrogen and simultaneously 12 liters of methane from each kilogram of solid waste. Then, additionally, we obtain 1 liter of methane in methane tanks. And from each liter of filtrate, we obtained additional 1 liter of methane. What about the purification of sewage from the toxic organic compounds? The initial concentration of end products of solid waste degradation was 2000 ppm in calculation for total carbon. And due to the sequential anaerobic degradation and in methane tanks and then additional purification in air tanks, we obtained the dissolved compounds 100-fold decrease. And due to the close technological cycles, you can see it is illustrated but by yellow sticks. This closed cycle led to this very suitable results. Next step, we must evaluate the possible ways of optimization of chromates compounds detoxification. And among more than 100 possible reactions with different chromium compounds, we choose only one reaction. It means it marked by green color and means irreversible reduction of chromium 6 compound chromate to insoluble chromium 3 hydroxide. And here you can see the comparison of the redox potential of low potential hydrogen fermentation, minus 415 millivolts, and high potential reaction of chromate reduction, plus 455 millivolts. And it is obviously that there's a very large difference between the donor system, that means hydrogen fermentation process, and acceptor process. It means the reduction of chromates is very large and close to 1000 millivolts. Additionally, we obtain the confirmation of potential possibility of existing and grows microorganisms at super high concentration of chromium 6. Why so? Because we postulated, and then during 30 years we confirmed the very important position. If the redox potential of reactions is inside of the zone of thermodynamic stability of water from plus 814 millivolts to minus 415 millivolts, it is theoretically possible growth of microorganism. And at the down left picture, one can see the confirmation of this theoretical position, the growth of Antarctic microorganism at the super high concentration of chromium 6 compounds. Let us return to the process of the fast hydrogen fermentation and degradation of model solid waste. Here you can see that we used potato and sugar beet. We tested and optimized our technological purpose in direct flow installation. And in the section from 1 to 4, simultaneously took part two processes. First of all, hydrolysis and hydrogen fermentation of solid waste potato, and simultaneously irreversible reduction of chromate to chromium 3 hydroxide. And in the next section, from the 5th to the 10th, we obtain the purification of wastewater from soluble organic compounds. So the coefficients of degradation were very large. Coefficient of degradation, it means the ratio of mass of initial waste to final mass. And here you can see that during only not more than 6 days, we obtain the maximal mass decrease in more than 500 times. And I will remind that in the spontaneous process in the dumps at 10 years, one can obtain the mass degradation of solid waste only in 2 times. So here you can see the confirmation of the suitable application of thermodynamic prognosis for practical application in biotechnologies. Here one can see the thermodynamic calculations that confirm the effectiveness of applying obligate anaerobic low potential microorganisms for fast reduction and precipitation of chromate compounds. And it is obviously that in this system microbiome of anaerobic microorganism used as a donor system and high potential acceptor system. It is chromium 6 compounds. And the energy yield of these two combined reaction is very high, close to minus 70 kilojoule per mole. But unfortunately, we obtain the negative result due to the specific properties of anaerobic microorganism. The normal growth and effective growth of low obligate anaerobic microorganism need very low redox potential, minus 400 millivolts, and ejection of chromium 6, it marked by blue color, lead to the jump, increase the redox potential to the positive zone from minus 300 millivolts to plus 230 millivolts. And it is obviously that lead to the blocking of metabolism of obligate anaerobic bacteria. And in our installation, the maximal concentration of suitable concentration of chromium 6 compounds was not more than 25 ppm. But on the basis of a thermodynamic prognosis, we choose the effect of stereometric redox gradient. Here one can see the visual model of this confirmation. In the usual vessel, on the surface of medium take place the growth of aerobic microorganisms. And as an indicator of changing in redox potential, we used resurinate sodium and bromethymol blue. The specific features of these indicators at minus 500 millivolts, resurin change its color from violet to red. And then from the minus 50 millivolts to minus 100 millivolts, it became colorless. The properties of bromethymol blue. It has a green color at redox potential higher than minus 200 millivolts, and BTB, bromethymol blue, became colorless at the potential low than minus 200 millivolts. And here you can see that independent of contact with atmospheric oxygen, 21%, the aerobic microorganism consume fast and effective, consume the oxygen, and even on the surface of this bacterial film, we obtain the redox potential not higher than minus 50 millivolts. And then in the middle zone of this vessel, we obtained deep anaerobic conditions, minus 200 millivolts and more negative. So only on this very simple example, we can see the possibility of regulation of redox metabolism and creation of redox gradient from plus 200 millivolts down to almost minus 400 millivolts. Let's give the short definition of stereometric redox gradient and redox locality. Redox gradient, this is a distribution in space of the reductive gradient created by metabolically active bacteria. And distribution and spreading of redox gradient is a function of the change in redox potential, in time, and in the volume. And the redox locality is spatial characteristics of both the reductive solid phase itself with coordinate x, y, z, so on, and its position in the limited phase, for example, in wastewater. And here you can see the illustration of forming of redox locality and redox gradient. On the left picture, one can see the whole bubbles of potato, and during the growth of microorganism, the cells penetrate inside of this potato, and final results of this metabolical process, blowing synthesis of gases and products of hydrogen fermentation, such as the mixture of hydrogen with carbon dioxide, and simultaneously very low potential soluble reductants. And on the right side, down picture, you can see the fast spreading of redox compounds. They marked as RH2, means the reductive compounds, out of the potato. So let's summarize that the redox locality and redox gradient give the possibility to reducing of toxic chromate compounds without direct contact of anaerobic microorganism with these high potential compounds. And here one can see the illustration of forming of the redox locality and redox gradient in the tube. In the middle of this tube, one can see the solid phase that consists from the solid waste and metabolically active microorganism. And obviously, due to the spreading of redox metabolites in the tube, we obtain the decrease of redox potential, and connected with it fast and effective precipitative reduction of chromates. And here you can see step by step changes in process. At the beginning experiment, the redox locality was on the down of the tube, and on the second third day, you can see that the moving of the saturated and low potential phase up to the tube, and simultaneously the reduction of chromate compounds. And on the right picture, you can see the zone of the reduction of chromates without contact of bacteria. On the down part of the tube, one can see the solid phase that consists of fermented potatoes and mixture of microorganism, and the gray zone, it is zone of the reduction of chromate without contact with cells of microorganism. And in the upper level, you can see the zone of soluble chromo 6 solution. And here one can see the confirmation of the effectiveness of applying of this redox gradient and redox locality, because in time of full complete precipitation, reductive precipitation of chromate, it was not difference between the concentration of 100 ppm of chromo 6 and 1000 ppm only in one day, we obtain the complete reductive precipitation of chromate. And it means that anaerobic microorganisms were completely isolated, spatially isolated from the super toxic high potential chromates. And here you can see the graphical confirmation of this effect. So then we investigate that the minimal effective size of the zone of redox locality. Here you can see the illustration of this scheme, and we use resazurin for obtain the changing without changing in redox potential in process of fermentation. And due to the direct measurement, we obtain that result that the 3 centimeters in diameter of this redox locality is enough for effective and long time reductive precipitation of chromate. One can see the very low potential minus 400 millivolts at the suitable pH more than 6. Well, here you can see the summarized model that inside of the redox locality take place the hydrogen fermentation and microorganisms are isolated from the dead zone that consists of toxic chromate, and in the middle zone it marked by a brown color. One can see the process of without contact reduction of chromates by microbial low potential metabolites. On this picture, one can see the all possible mechanism of metals detoxification of by a microorganism. There are sorption, reductive precipitation, and so on. They are rather well known, and I will not pay your attention. But due the practical applying of this conception of redox locality, one can see that redox locality and microorganism metabolically active can realize all possible mechanism of interaction with toxic metal compounds. And here you can see the reductive process of chromate precipitation, then precipitation of Kappa2 cation due to the synthesis of hydrogen, precipitation of thin cations by the biological origin carbon dioxide, and so on. And finally, you can see the total model of without contact detoxicative processes of metals precipitation. So you can see the graphical illustration that in direct flow installation from the beginning, from the first section and to the end section, one can see irreversible precipitation of wide range of metals. But this redox locality gives the possibility not only to use this method for the purification of wastewater from only metals, but also from radionuclides, because due to their chemical properties, they are very close to the toxic heavy metals. And it is obviously that redox locality will give the possibility the successful suitable precipitation radionuclides together with non-radioactive metals. And it is obviously that it is true for the different xenobiotics, on the example of nitrochlorobenzene, because without contact reduction of unsaturated connections in aromatic ring lead to the anaerobic reductive pathway degradation of these xenobiotics, very toxic and stable for degradation. So let's summarize. The new approach of redox locality and redox gradient gives the possibility for the practical realization approach for the microbial detoxification of wide range of xenobiotics. That means heavy metals, radionuclides, and organic xenobiotics without direct contact with microorganism. And so it gives the possibility for the further large scaling and application of our approach. Here you can see our scientific team, and that's all. Thank you very much for your attention.